The next question. This is the next question. I guess the first part is said define or state L'Hopital's rule. L'Hopital's rule states that if the limit of a function is an indeterminate form, note that is by direct substitution. If they give you a function, setting it to a point, and you directly substituted that thing, and then you are getting indeterminate form, which is 0 over 0 or infinity over infinity, then by L'Hopital's rule, the limit of that function they give you will be equal to what? The limit as s tends to the point of first the derivative of the numerator over the derivative of the denominator, provided that the limit on the right exists. You know the limit on the right exists. That is, provided that this limit here, the limit, we have the left hand side, provided that the limit here exists. The limit where we put the derivative. But if the first derivative it doesn't exist, you go for the second derivative, you go for the third, you go for the fourth. For those of you that don't know what the theorem is all about, this is L'Hopital's rule. This is the theorem. This is the theorem. Now we want to use that. Since they've given us a premise, the conclusion is that they want us to use L'Hopital's rule to solve this question. Now what do? Let's go and solve the question. Limit as s tends to 3 of what? S cubed minus 27. Limit as s tends to 3. Limit as s goes to 3 of s cubed minus 27 over x squared minus 9. First thing, by direct substitution, because that's what the theorem states. We need to substitute it directly first. So that will be what? Some of you don't say, but by direct substitution, I already know it's going to be 0 over 0. Hey, do it. Let's see it. Don't assume the teacher will know. Don't assume the lecturer will know. If you don't do that, we may actually claim some of your mark. And you get what I'm saying? Don't assume anybody knows anything here. Do it first. So this is going to be what? 3, substituting 3 for x. That will be 3 cubed minus 27 over 3 squared minus 9. 3 cubed is 27 minus 27 over 9 minus 9. Somebody saying then we get 0 over 0. This is an indeterminate form. Then since we've stated L'Hopital's rule, there's another thing we can do to this. It's not always L'Hopital's rule. We can actually factorize this. But then once again it may be stressful. So let's just go by L'Hopital's rule. What does that rule state? That the limit of this thing will be equal to the limit as s still go to the normal point of the derivative of the numerator over the derivative with respect to x of the denominator. Are we alive? Obviously, 100%. So this is going to be equals to the limit as s goes to 3 of what? Definition of a constant is 0. Let me change my ink right here. Definition of a constant is 0. Definition of x cubed, that will be what? 3x squared over. Definition of a constant is 0. Definition of what? 2x squared is going to be what? That's sorry, I said 2x squared. Definition of x squared is going to be 2s. Sorry. Definition of x squared is 2x. Now we cannot apply as that. We cannot go by direct substitution. That anywhere you see s, put 3. So that will be 3 into 3 squared over 2 into 3. And that is what? 27. 3 squared, that's 3 times 3. 9 times 3, 27 over 2 times 3, that is 6. And that is still 3 here, that's 9 over 2. That is what the limit will yield. Now listen up, let's assume upon this substitution we still get 0 over 0. You apply L'Hopital's rule again. There are some functions we have to apply the L'Hopital's rule like twice, like 3 eyes, for we to be able to get something beautiful, for we to get what they actually wanted us to get from the question. Example of such function, let me give you here in case you can go over it yourself. Example, let's say I say limit as s goes to 0 of let's say cos 2x. No, let me not make it cos. Let's say I put 3 sine 2x over x squared. 3 sine 2x over x square. Am I getting this thing right? That's 0. That's 0.0. So when you do this, I think the first instance, will you get something beautiful? There are some of it upon first instance you get something beautiful. Some of it, you try the first instance, nothing is working out. And then you apply L'Hopital's rule again for you to be able to get the function you need. So at times you apply L'Hopital's rule twice, thrice before we get actually what we need to get from a given expression. Are we together here? Thank you. Now we are told to equally verify the continuity of this function at s equal to 2. You know, this function here, we have two different functions now joined together to give us another function. Now the two functions, glory be to God, they are polynomial functions, one quadratic function, the other cubic function. Now naturally, I think it is not rational, like it is not fraction in nature. It's not something over another thing. Do you understand? It should have been continuous at every point. Now, but once we have a fraction, there is a point it will not be continuous. Once we have an algebraic function that is rational in nature, like it is in fractional form. Do you understand? Now, there is a point to which the continuity of that function will definitely be altered. It will be altered somehow. Like there will be an halt to it. Now, what they say function is continuous. If you draw the graph will continually flow like a stream. It will continually go, just like a quadratic graph. It will continually go up or continually come down. Let me explain what I'm talking about. Like if you have a continuous function, the graph will always go like this, just continuous. And if you keep giving yourself negative value, this one will keep going off. Giving yourself positive value, this one keep going off. That's what I mean by a continuous function. But if it is at a point that it is discontinuous, let's say it is discontinuous at s equals to 2. Let's say this is point s equals to 2. It will come like this, get to that point. Oh, sorry. Then it will, let me clean it. It will get to the point. And then from here, very good. There will be a loop, like the loop I created here. There will be a loop around here. That's what I mean by discontinuity. So we say that is the point of discontinuity of the curve. In case you haven't visualized it here, you don't hear okay, continuity. This is an example of a continuous function this is a graph of a function that is continuous at everywhere, and this is a graph of a function that is continuous at everywhere, but s equal to 2. At every point in real number it is continuous, but it's not continuous at the point where s equals to 2. Now that's an example of continuity of function. And for some of you that are thinking, where do I get my question from? Let me show you. This is the question right here. For UI students. This is 2016-2017 question, and that is right there in number 1BIII. The first question we've solved, L'Hopital's rule, 1BI, limit of a function, 1BII. This is 1BII. Are we together here? Now we want to check the continuity at that point. Is it continuous at that point? And there is 3 things you check out for. If you say okay, check for the continuity of the function at a particular point, all you want to check for, number 1, is does the function exist at that point? Like, is the function defined? Is the function defined at that point? You know, naturally now, since you have a rational function, there is a point to which that thing is not defined. That is the point where the denominator equals to 0. So, but then, is the function divided at that point? That's the first thing. Now, if the function is divided at that point, the next thing you check is that does the limit as s approach that point exist? That is the limit as s tends to, the point here is 2, of this O function, does it exist? Now the next thing we now check is that, is this limit equals to f at that 2? The limit as s approaches 2, is it equal to f of 2? If that 3 conditions are satisfied, then we say the function is continuous at that point. But if it fails at any point, then it is discontinuous. The first thing is check if it is defined. If it is not defined, then no continue. The next thing, check the limit. If it is defined, it passes that test. You write the answer. What is the definite answer it gives me? 1 over 2, minus 2, minus 5, minus 7 over 4, minus 2 over this, minus 0. Sorry, there's nothing like minus 0. 0, just a definite answer, a definite answer. Now, if you've gotten your defined answer at that point, the next thing, check the limit. If the limit you got is not equal to, if the limit does not exist at that point, number 2 thing, you don't continue, then the function, it will not be continuous. It must pass every state. Now, if the limit exists, now go to the third step. Is the limit equal to what you get in the first step? If it passes first step, it fails second step, it will not pass third step definitely. If it fails first step, you don't need to continue. The point it fails in either of the two, don't continue. But the third step now, let's assume it passes step 1, it passes step 2. That point, checking continuity. Now, the step 3, these are what I call step 1, step 2, and this step 3. Now, if it fails step 3, although it passes step 1, it passes step 2, but that doesn't mean it's continuous. It is still discontinuous still. So let me continue. I just need to explain the process, the idea to you guys, so that you not be like we are just solving and we don't know the reason we are doing this. There's a reason we do that. We just want to teach you that at times there are some curve you drop in mathematics, you draw some curve, and actually at some point you notice that it is not continuous, it cannot go, and then you can still get other values such that you can trace it, but at that point there will be a loop. That loop is a point of discontinuity. Just get that clear. Now, how do I get f of 2? If it is divided and that 2, of course, if f of s equal to something, f of 2 will be what? Anyway, you find s, substitute 2 for it. Are we together here? So we have numerator thing, denominator thing. Substitute 2 into the numerator, substitute 2 into the denominator, and let's see how it goes. For the numerator, we have 3x squared minus 7s plus 1. That will be 3 into 2 squared. That's what I have here. 3 into 2 squared minus 7 into 2 plus 1. So simplifying the numerator, 2 squared is 4. That will be 3 times 4 minus 7 times 2 plus 1. 3 times 4, 12. Minus 7 times 2, 14 plus 1. And then 12 minus 14 minus 2 plus 1 minus 1. So that is that. Now the denominator, that is 2. That's 2x raised to power 3. This is the denominator right here. This point. Very good. Now, that's 2x raised to power 3 plus 4s squared minus 11. 2s raised to power 3 plus 4s squared minus 11. Now you want to check the point. If f of 2 exists at that part for that one too. So all you need to do is just to put 2 into the function here. Put 2 there. So that will be 2 into 2x raised to power 3 plus 4 into 2x squared minus 11. If you continue, simplify where necessary, you get 21. So it is even at that point, because our f of 2 is actually the numerator minus 1. Sorry, let me write it the proper way. Now f of 2, I'm coming, let me just make room for it. So f of 2 is minus 1, which is the numerator, over 21, the denominator. So it is divine. It may be fraction, it may be negative number c. So far it is number, even 0. It is divine at that point. Are we together? If it is not infinity. For infinity, it is not divine. A limit can tend to infinity. But you getting a definite value, infinity is not a definite value. Note that. Do you get what I'm trying to say now? So that is the first part. The next thing you do is to check the limit as s approaches 2 of that same function. Limit as s approaches 2 of that same function. What do we mean by that? That was what we did here. That's what we did here at the start. Don't mind me. That's what I have here. The limit as s approaches 2. That's what I have here. Limit as s approaches 2. What do you need to do? If you have limit as s tends to something, just go by direct substitution. And if you go by direct substitution, it will just be as though you are going for f of 2. Now, but there's something about it. The thing about this is that now, at times we have seen scenarios that the limit will be different from direct substitution. That's if upon direct substitution you get some things and the limit may be different. There are situations like that. But in this situation, we substituted the limit. That's 2 for x, both at the numerator and at the denominator. We get what? The limit as s approaches 2, as s goes to 2, is what? The limit at that point is still minus 1 over 22. Now, you notice that we conclude that f of 2 is divine because we get a value. And the value is what? Minus 1 over 22. The next thing, the limit exists. We get a definite value. Be it, in fact, we can equally get infinity for limit. We can get 0 for limit. That's all divine. But actually, we get minus 1 over 21, which is actually a divine value. Now, the next thing is that we eventually get to know that the limit is equal to f of 2. F of 2 we get minus 1 over 21, and the limit we get minus 1 over 21. So the limit is equal to f of 2. Hence, the conclusion is that f of s is continuous at x equals to 2. That is the conclusion we draw to that question.